In order to properly study trends in physics and in science, we need to have properly calibrated equipment. So, as for the world of temperature, how do we exactly calibrate a thermometer? It's actually fairly quite straightforward. As long as you have a container filled up with water, and I did have ice cubes in here earlier, and you let it sit there for a while, it will stabilize at 0 degrees Celsius. So as long as you have an ice water slurry with no other contaminants in there, that's 0 degrees Celsius. How do you get to 100 degrees Celsius? As long as you have pure water and it's not a rainy day or a super sunny day, so you're at regular ocean level air pressure at 101.3 kilopascals, then the water will boil and stay there at 100 degrees Celsius. So that's how you calibrate a thermometer. Put it in ice water, let it sit, put a marking down here. Boil that same solution now, let the temperature stabilize. As long as you're not in the mountains, it will stabilize at 100 degrees Celsius. Divide that by 100, and now you got something measured in degrees, portions out of 100. All right. However, that system over there is only certain to the nearest degree Celsius. But in science, we want to have an even more precise ruler. So how do you measure it to fractions of a degree Celsius? Well, then you need to find a very specific temperature and use that as your reference. And it turns out that point does exist, and it's pretty trippy. What you see here on the right-hand side is known as a phase diagram. A phase diagram just simply tells you that depending upon the pressure you're at and temperature of the solution, you can anticipate a certain outcome in your experiment. So normally we're at 101.3 kilopascals for our air pressure. Sometimes, just to make life easier, scientists like to normalize numbers. So that's normalized to the value of 1. So 1 atmospheric pressure is 101.3 kilopascals. Obviously, if you double 1 to 2, then you're at 202.6 kilopascals, so on and so forth. So we got that part knocked down fine. Well, we also know that at regular atmospheric pressure, water begins to boil at 100 degrees Celsius. And I did mention last day in the homework solutions that you can actually have water boil at lower temperatures. And all you need to do is simply remove air pressure from it. Water molecules are jiggling around. Now, water does want to turn into water vapor naturally. If you drop water on the table, you'll notice that over time the water will evaporate. But with 300 kilometers of air squishing down on it, it makes it tough for it to evaporate. So you remove those conditions. You remove the 300 kilometers of air, and you'll see the water will quickly want to boil off. If you ever have a chance, check that out as a demonstration your teacher might show you if you're a nice and polite student. I've done it before. So I hook this up to a vacuum pump and I suck it away, and this starts to boil as you would visually see it. I'd have a student hold on to it, and the student might be afraid of it because they think it's really boiling water, but remember, boiling is just a state change. It's conversion between liquid and gas. In fact, there's an interesting temperature and pressure that exists where you can't tell the difference between this being water, ice, or water vapor. I hope the video plays. Here it goes. All right, and if you watch this for long enough, you'll see bubbles, you'll see a sheet of ice forming, and obviously below the sheet of ice, the water is still there. And this only happens at a certain pressure and at a certain temperature. And it's known as the triple point. And that triple point can be calibrated to the nearest hundredth of a degree Celsius. There you go. I don't want to copyright strike, so I'm going to stop it right there. So yes, water can exist in 3 states all at once, at a particular temperature and at a particular pressure. So by going to that, now you can calibrate your thermometer to the nearest hundredth of a degree Celsius. Yes, they sell those thermometers. Go check it out at the drugstore. They do sell it there. Double the price. So the study of temperature is known as calorimetry. All right, the temperature in a given substance. Now, with regards to water, we can figure out how much effort it takes to heat up water. All we need to do is put a paddle in there and figure out how many joules of effort we took to increase this by degrees Celsius. And it turns out that works out to roughly 4218 joules of effort to increase a kilogram of water by degrees Celsius, or half that value for 500 milliliters of water. But how would you figure that out for other substances like metals? After all, metal's not a liquid and you can't exactly stir metal around. Well, calorimetry relies upon our understanding of Q plus Q is equal to 0 joules. If energy cannot be created or destroyed, then as you heat up one substance, the other substance must cool down, and they will stabilize to a certain final temperature. That will give you sufficient givens to find out the outcome.
Heat, or thermal energy.
I don't want a copyright strike. All they did was drop a really hot piece of aluminum into water, and it stabilized at a final temperature, and these are the values that are observed. It was 100 grams of this mystery metal, which was aluminum. It started off at, or the water started off, do I have it listed over here? The aluminum was heated up into the point where it reached 153 degrees Celsius, and then it cooled down to 35 degrees Celsius at the end of that video. The water started off at a cool 22.2 degrees Celsius, and it heated up to a final 35 degrees Celsius. That actually gives us enough information so that we can find out the specific heat capacity of the aluminum itself. So you go through all the number crunching. If you want to pause the video, go ahead. And here's the reveal. You'll find out that the heat capacity of this particular isotope of aluminum worked out to 910 joules per kilogram per degree Celsius. There's a fancy device called a bomb calorimeter. If you've ever been curious about how much nutritional information is in a particular food substance, this is how they do it. Doesn't work so well with regards to this guy over here, but with solids like a potato chip, they'll place a potato chip inside a container filled up rich with oxygen. There's a little ignition wire. As long as you pass a high voltage through this, the ignition wire will cause the potato chip to catch on fire. And once it catches on fire, that thermal energy is released onto the container, but it's also absorbed by the water that's inside the bomb calorimeter. Now, the bomb calorimeter needs to be insulated because we don't want to do more calculations factoring the container. Not only that, we don't want this to be an open system because then it'll be near impossible for us to figure out what the heat capacity of the potato chip is. So really, the amount of thermal energy used to heat up the water is the heat capacity of the substance itself. Yes, another YouTube video. I don't want to play it, but what ends up happening is that this professor burns a donut, and Homer's not happy about it. So how many calories was in this donut here? Go ahead, try it out yourself. Once again, we're not really concerned about the heat capacity of the donut itself. We just want to know how much thermal energy it gave off to heat up the water from 24 to 94 degrees Celsius. So, Q is equal to mc delta T. The bomb calorimeter had 3 kilograms of water. Heat capacity of water is 4190 joules per kilogram per degree Celsius, and the water increased from 24 degrees Celsius up to 94 degrees Celsius. 94 subtract 24 will give you 70. Multiply that all out, and hopefully you got 879.9 thousand joules. A nutritional calorie is equal to 4184 joules. And yes, it has to be a big C. Trust me, there's a difference between a calorie and a calorie. A calorie, if you're curious, well, you have to go off and get 1,000 of them to equal 1 nutritional calorie. And the only difference between these two is just a lowercase and capital C. And that's why there are certain countries, especially in Europe, that can't be bothered with this silliness, so they'll just call this simply 1 kilocalorie. Go ahead and check it out on any international food package. They'll measure it as a kilocalorie, as opposed to this strangeness of a capital C, meaning 1,000 calories. Now you know. Here's an interesting challenge question. So, you take an object and you grind it against the ground. Obviously, you're going to generate a lot of friction, and that friction can cause the substance to increase in its temperature. So, let's go and figure that out. In this situation over here, the amount of thermal energy gained by the work due to friction is equal to 0 joules. Remember, this is an isolated system. So Q is equal to mc delta T. And the work due to friction is equal to initial speed. I suppose in this case over here, work is equal to delta EK, which is equal to 1/2 mvf squared minus 1/2 mvi squared. You have an initial speed of 10, final speed of 0. I'm pointing out that I'll make it a minus in here. So it'll be equal to plus negative 1/2 mvi squared is equal to 0, where when you bring this over to the other side, you have mc delta t is equal to positive 1/2 mvi squared. Beyond here, hopefully you can solve for your TF. Here's the full reveal. And now you know. For more fun and adventures like this, how about you try out this challenge question here? You have an ice water slurry problem. So, ice is dropped into the water, and the question is, what is the final temperature? It's pretty messy, because even though the water temperature may gradually decrease and stabilize, the ice has to do some few extra steps. First off, you got to bring the ice up to the melting temperature. Then, once all the ice is melted, the temperature will finally increase until you stabilize to whatever your TF is. So you have the lemonade and you have the ice. A lot of things are going on. Lemonade only has one equation, which is Q is equal to mc delta T, but the ice is going through quite a few things. First, yes, it has its Q is equal to mc of ice, which is roughly at 2000, and then you have a final temperature of 0 degrees Celsius, and it started off at 10 degrees Celsius, or negative 10 degrees Celsius. Then you have to take care of the Q is equal to mLF, positive because you're melting the ice cube. And then for this one over here, you have Q is equal to M, heat capacity of water, final temperature we're looking for, but don't forget start off at a frigid 0 degrees Celsius. As for lemonade, you have the mass of the lemonade, you have the heat capacity of lemonade, which is close enough to that of water, and the final temperature you don't know of, but it did start off at an uncomfortable 27 degrees Celsius. Too warm for my comfort. So, what is the TF? If you want to pause and work it out yourself, go ahead. But here's the answer, in case if you're curious. Keep on trucking along with your homework. I'm sure you'll make it there. Now, as for the homework itself, question 1 you should be able to do. Here's the answer. Question 2 you should be able to do. There's the answer. Question number 3, I think that's the limit for what a grade 11 student should know. But if you're really interested in this stuff over here, by all means, challenge yourself out with question number 4 and question number 5. Because physics is fun. Catch you later.